All right. First of all, thanks a lot for the invitation to come here to this conference. I'm going to give, I guess, a bit uncommon presentation for a developer summit. I'm going to talk about mobile network insecurities and what we can learn from them. There's going to be no new research or vulnerabilities in this talk. Rather, I'm trying to give you a very simplified overview of the design decisions and their consequences, in particular in GSM networks, as I assume that most of you are not mobile network or mobile network security experts. If you are a mobile network security expert, you will notice that I am explaining things very to get to the root cause of the issue and not to explain every single vulnerability in detail. So I'll talk a bit about what people were trying to achieve with security mechanisms and where they made mistakes that had very significant consequences. So why are mobile networks so interesting to us? I mean, they are ubiquitous. We have them everywhere. And if we find vulnerabilities in them, they are usually very hard to fix. So let's look at what a mobile network means to us. So it's a very simplified overview of the network structure. It's a distributed network, so it more looks like this. You have a lot of base station transceivers, base transceiver stations that your phone connects to, and you have this little thing in your pocket, and then receive and make phone calls. No wires attached unless you want to charge it, and this works for about 20 years now. If you look at it from the perspective of engineering, this is quite a very complex architecture that has solved a number of problems. So first of all, we have the challenge of scalability. How does this work, right? You have a country of the size of China, countries of the size of Germany, and you put a mobile network in there and it works, and you have millions or hundreds of millions of users in these networks. So scalability is a huge challenge when you build something like this. And you have the other requirement, which is reliability. Nobody's going to tolerate that the mobile network doesn't work. And then you build this thing, you spend millions of, hundreds of millions, thousands of millions of dollars to build the mobile network. So your main threat, your main concern when you build the network is your failure to monetize it. So fraud is your main concern. As I said, you can travel around and your mobile connects from cell to cell and just you have a steady communication, a steady call. You can receive incoming dials my number now, it will ring, even though I just recently came here to Hong Kong. So there's a lot of engineering issues that needed to be fixed. Now, let's look at the threats. When we talked earlier about how I recommend to think about security, I said, don't only think about the threats that you are concerned with, also think about the attacks that other people may think of. And usually the targets of these attacks are your users and not particularly yourself. So in mobile networks, we differentiate 3 common attack types. The first one is the tracking attack. So somebody discovers a user's location. I want to know, and I know that there is one entity in the world that does know it, and that is the mobile network. If you think of it, it makes sense. If you look at a country or just a city the size of Hong Kong, let's say I operate a mobile network here, and I have, I don't know, a couple of million users. Now, a significant number of my users are going to receive a phone call every given second. So I cannot alert at the same time. I would just immediately overload my network. That means my mobile network needs to track the whereabouts of users to make sure that when they have an incoming transaction, only the antennas in that vicinity call for the user. Otherwise, the thing just wouldn't scale. So the mobile network always knows where you are. The most common and the most obvious attack type, of course, is phone intercept, right? Somebody listening to your calls. or reading your short messages, or intercepting your data traffic. And the last one, the last attack type, and unfortunately, apparently the only one that mobile networks really care about, is impersonation. That means not only do I know where you are, not only am I able to intercept your transactions, I am also able to make transactions in your name. So for example, place a call on your behalf, send a premium SMS on your behalf. Premium SMS are short messages that you pay for per message. Oftentimes they're used to pay for rather dubious services or to donate money to charity. So let's keep in mind these three attack categories while we the most obvious one, of course, is the radio interface, the waves that are in this air, the ones that are hopefully encrypted and can't be read by anybody. We'll see about that. The second one being the SIM card, the little module that you have in your phone. And the third one being the interconnect. I'll dive into each one of these a bit deeper. So if we look at this simplified network, at these simplified schematics, the air interface or the radio interface, as I said, is just in the air. Our mobile phones transmit lots of data, and we want to see if we can intercept these. So the first attack on the first GSM intercept attack that became publicly known was the idea of a fake base station. So as the mobile networks had fraud as their main concern, they strong authentication scheme to see that only legitimate users can authenticate to the network and are then offered services, right? If you are a customer of mobile network A, you will not be able to connect to mobile network B. Mobile network B will just not offer services to you because mobile network B wouldn't know how to bill you. So as soon as you have an identity that can be charged, mobile networks are happy to provide service to you. In order to accomplish that, they build a very strong authentication scheme that users can connect to the networks and others cannot. However, they didn't very much consider that their users could also connect to illegitimate networks. So while the network does the best it can to authenticate the user and make sure that this is a legitimate customer of the network, the standard does not include a lot of authentication. Connects to basically any network that's out there and tries to connect to it. And it's left to the network not to provide the service if they choose not to do so. There was one complication that basically also what I think is one of the application into the phone in the first waves of mobile networks, and that is your mobile phone is supposed to work all around the world. My mobile phone, when I travel to Hong Kong, connects to a Hong Kong network flawlessly and doesn't complain about anything. But the vulnerability that was introduced this way in the GSM standard is that basically anybody can offer a mobile network. And the phone will always connect to the strongest cell tower in its vicinity. So the attack works as follows. I operate a mobile network, and I just pretend that I am the mobile network that your mobile phone prefers. These are only a few bits that I have to set in my mobile network configuration, which is the MCC and the MNC, mobile country code, mobile network code, a couple of other parameters, and your phone will fake base station. By the time the mobile connects there, my fake base station will do a couple of things differently than the legitimate network would do. For example, it just tells them, okay, you're authenticated, everything is fine, and today we're just not going to use encryption. So if you want to make a phone call, no problem, I can offer you service. You just hook up the thing to let's say, an external service provider, voice over IP service, or something like, and you can easily provide outgoing calls. Also, you can collect information about the identity of the users that have connected to your fake base station. So for example, you would put up a fake base station near a demonstration, and everybody that attends the demonstration is collected by your fake base station, and later you can see who was there at the point in time. There's one big problem with fake base stations, and that is they usually do not offer a possibility to receive incoming calls. That is a problem for the users that don't receive the calls, but also for the attackers that might want to intercept incoming calls as well. So at least theoretically, they can steal the authentication messages from their victim and then authenticate to the acting as a man in the middle. So the fake BTS connects to the network as you, and it provides the network service to you again, dropping all kinds of encryption or security measures that may have protected you before. But this is, to some extent, 90s, early 2000s stuff of type of attacks. Attackers have built much better capabilities here. But again, just to summarize, this way you can track users by collecting their IMSIs, their mobile subscriber identities, and the equipment identifiers, so the serial number, the unique serial number of a phone. Or you can intercept incoming and outgoing transactions if you see fit. All that is possible only because of the failure to have some mechanism to make sure that the mobile equipment can also authenticate the network. But as I said, attackers have moved forward to more elegant attacks. One of them being the passive intercept, which means instead of having some kind of active radio transmission in the air and a device that you have to set up, you just passively sniff radio transmission signals from the air and decrypt them later. In most countries of the world, GSM networks operate in an encrypted mode. I'm sad to say that in this area, this is not the case. Let's assume that your mobile network was using encryption. The encryption that was built into GSM was not that bad of an idea. It's a stream cipher of 64-bit length, and it's applied to the GSM frames, which are basically small chunks of transmission organized manner that enable the base stations to handle several users. So with the key lengths of 64-bit, there was, of course, a first mistake in early implementations of SIM cards, where the effective complexity was reduced to 54 bits. And that is near the level where you can actually attempt cracking attacks just without any major efforts anymore. But as I said, in general, the cipher is not as bad as it seems. It was made worse, though, by violating some fundamental principles that apply when you use encryption. When you encrypt contents, you want to make sure that an attacker cannot guess the contents of your encrypted messages. And this principle was violated at several occasions in GSM specifications. For example, not always would the information that is supposed to be transmitted between the base station and the mobile equipment exactly fit into GSM frames. So you would put information into several frames, or the information would not fill the frame. And the standard behavior in this case was to just fill up the frame with predictable information. So you would just put null bytes in there or 2f, 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 2f to just fill the frame, right? The specification says there is a frame, this length. If your information is shorter than that, you just fill it up with something. We don't care. So for reasons of efficiency, those frames were filled with predictable information. And that again enables an attacker to see, okay, I know the contents of this message partially because I know that the end is going to be the same padding every time. Also, certain messages with little entropy were transmitted unencrypted and encrypted as well. And those are the system information messages of type 5 and 6. And there were several other empty GSM frames with very little entropy, little to no entropy. So what this means to the attacker is that you have a GSM frame of the full length and a predictable content. So you know that every change in that GSM frame is due to the attempt of encryption that was made to that GSM frame. And if you have collected enough of this plain text, it enables you to calculate backwards to how the stream cipher that was used in this case was initialized with a key. See, that's where we come to the point where it's getting a bit more complicated. I'm hoping not to lose you. But I think the general principle should be clear. If a message is encrypted and you know the contents, you can derive the way it was encrypted. With 54 or 64 bits of complexity, you still have a lot of different outcomes that your encrypted message can have. So it's impossible, or it would, yeah, it's virtually impossible to just write a code book. A code book would be a book that says, this is the encrypted message, this is the key that created this message. And you just write all combinations down, and then you see an encrypted message and you derive the key. So what attackers, they built so-called rainbow tables. And rainbow tables are a way to make it much easier to implement a code book. So I start out with plain text with a random key. And I know the encryption function, right? So the result is a ciphertext. And that would be the encrypted message that I would assume to be sent over the air when this key is used. Now, this ciphertext I just take as the next random key and encrypt the plain text using that key again. And then there is again, of this message, use it as another key and encrypt the plain text again, building a chain. And now I only store the initial random key and repetitions of the same encryption procedure. So while I'm storing only the random key and the ciphertext that I receive after n repetitions, I have a compression ratio of exactly the chain length, right? So if I repeat this 3 times, my compression ratio is 3 because I don't store the 2 intermediate results. So instead of storing all results in a codebook attempt, I'm only storing the beginning and the end of one chain that I've computed. And in doing so, I can drastically decrease the storage that I need for my code. At the same time, I am increasing my computation need because in order to crack a message, I create the chain n times, store all the results, and then look up one of these results and see if they are in my rainbow table as a result. And then I calculate backwards again until I have the actual key to my message. So I hope the general principle is clear, and this helped attackers in this independent researchers distributed in the world to create rainbow tables of 2 terabytes in size that you need in storage, that at the same time enable you to basically decipher GSM messages in real time, and still enable you to decrypt a recorded communication within a few seconds of lookup. And to fix these vulnerabilities, mobile networks needed to stop sending predictable messages. However, since they were in the standard, this was not so easy. One of the main were, instead of using predictable null padding, padding empty GSM frames with random input. That makes it impossible to create, and stopping sending predictable messages once encryption started. So this basically reduced the cryptographic attack surface, but these attacks are still possible in many networks nowadays. Second vulnerability in mobile networks, this time being much more interesting and a bit more simple to understand, I hope I'm not losing you here, is attacks on the SIM card. So who would have an idea why we have a SIM card? What's the reason a mobile network issues us a SIM card? Why do we have it? What's its purpose? Identity? Why is it not a letter? Why is it not a code that we type into our phone? Yeah, you can change the phone, but if I had a code that I can just type into my phone, that would be nice as well, right? The reason why we have these hardware security modules here, the SIM cards, is that mobile networks don't want you to deploy more than one phone. So they were looking for a means to make sure that you cannot clone your identity, or anybody else could clone your identity. And they built these little modules, these little chips that carry a couple of secrets in them. Your material that I don't want to bore you with, and that would never. Sorry. Okay, so there's the international mobile subscriber identity. That's the part that you don't want to that they don't want you to reuse. And there's 2 cryptographic keys, the KI and derived from that the KC, and lots of other configurations on the SIM card. And the idea of the SIM card is that it has one very specific super secret key that even the SIM card will never disclose to you, and the cryptographic function to messages that you send to the SIM card. So when you initiate a call and you authenticate to the network, the mobile phone would pass on the challenges that it receives from the mobile network to the SIM card, get the response, and hand it back. And the SIM card is supposed to be a module that doesn't, that as a consequence of that cannot be cloned. You need the SIM card. So that was the whole idea. Again, they were trying to protect themselves against fraud. Now, the SIM cards grew into much more than just the trust anchor of mobile networks. They grew into little Java virtual machines. So you could deploy small applications on the SIM card, which was a beautiful. Standards were written to make sure that the mobile network can communicate with the SIM card. So it's not only a hardware module that you put into your phone, it's also a computing environment that can be configured from the distance. So how would you configure the SIM card from the distance? Obviously, you would use the mobile network. So your provider, your mobile network provider, can send little short messages to your SIM card. Things. These messages are specified in a way that your mobile phone would not even alert you about them. So your mobile network can send a silent SMS, you're not going to be alerted, and reconfigure your SIM use this in cases of um, roaming agreement changes. So for example, when I enter Hong Kong, my mobile network in Germany sends a silent SMS to my SIM card saying, hey, you are now in Hong Kong. Please prefer, I don't know which network is it, CSL as the mobile network now, because we have nice that you can use as well. But if CSL is offered, please use CSL because that's economically the most profitable for us because we have agreements with them. So there are configuration changes like that that your mobile network can just issue to your SIM card. It can also deploy Java applications, small applications that run on your phone. These become very interesting in near-field communication payment, contactless payment. And you can deploy all kinds of files to the SIM card. So these are very interesting modules by now. And of course, they needed to think about, okay, how can we secure and the SIM card? And they realized, okay, of course, we're going to use encryption. And we'll make sure that the SIM card and the mobile network share a so-called OTA key. So this is the key that protects the communication for the over-the-air updates. And now they made a very unfortunate mistake. And that is they specified this over-the-air protocol quite nicely, but they didn't specify the error handling perfectly. So here's an interesting attack path that works on a number of outdated SIM cards that use the data encryption standard for. So I, as an attacker, attempt to send an over-the-air configuration message to your SIM card. And since I am an attacker, I am not able to sign it correctly. So I just put some random bytes instead of a signature. Your SIM card will receive the message and say, okay, this is a command. I understand the command. And there is a signature behind the command, but this signature doesn't check against the OTA key that I have. So I will not execute the command that you have sent me. Perfect. SIM card does exactly what it's supposed to do, reject the command. However, in my command, I told the SIM card, please, if you respond to me, make sure that you sign your message. And the SIM card now sends a generic, not authenticate your command, leave me alone. And a subset of SIM cards made the error that they would actually sign the message. And please sign the message was a command that was given by an unauthenticated entity and that was not signed. But the specification did not specify whether you should do it or not. So some SIM cards sent responses, some didn't. Very unfortunate mistake because again, we have a predictable plain text and that is the error message that I receive. And we have a DES signature. So again, we can do the same that we did before. We create rainbow tables. We have the plain text and we have the signature that's behind, that's given to the plain text by the SIM card. The consequences of this little mistake were grave because by just sending one unauthenticated wrong command to the SIM card and receiving the response, attackers can then recalculate the OTA key that gives them complete access to the SIM card, enabling them to install applications on the SIM card, enabling them to change configurations in the SIM card, and for some SIM card models, even worse, stealing the very complex secrets that are not supposed to be stolen from the SIM card by deploying malicious applications and exploiting vulnerabilities in the Java virtual machine that the SIM card provides. So again, a very minor mistake, just leaking cryptographic material at a spot where you shouldn't do it, and grave, grave consequences. So let's get to the third topic because I'm already being warned that I'm about to stretch my time here. The interconnect attacks. So mobile networks combine many technologies and attack surfaces. And one of the largest attack surfaces is the interconnection to other mobile networks. I mean, it's a great idea of engineering. I can use this wireless phone here in Hong Kong, call my friends in Germany, and they can answer the phone, and there is no wired connection between us. And the phone networks seamlessly interact. Somebody in Germany can send a short message to me, and few seconds later, it will be delivered here in Hong Kong. Very beautiful engineering approach. And I mean, this is, I don't know, to people that are a bit older than me or my age and older, they probably realize that this is a very fancy thing. But of course, some technological trade-offs needed to be made when this was set up. So as I explained earlier, the mobile network needs to know where you are in order to deliver messages to you. Now let's imagine somebody in Germany having a different mobile network than me. So I am a subscriber of mobile network B, and my friend is a subscriber of mobile network A. Now my friend is sending a short message to me. So this short message travels to the SMSC of his mobile network. And this SMSC will then approach the other mobile network, my mobile network, and say, hey, you know, I have a short message to your subscriber XY. Where can I deliver it? And my mobile network would then respond with, oh, he's currently at the following mobile network internal address. Just talk to this cell directly and deliver your short message. And that means that the mobile network of my friend then has my most recent cell ID and the current location area code. Today, that would mean they would see that I am in Hong Kong. Now, the normal way would now be that mobile network A sends me the short message and everything is fine. But of course, this can be exploited. You just send a query to any mobile network over SS7 and say, listen, I have a short message here. I want to deliver it to Linus. And the mobile network say, yeah, sure, he's in Hong Kong. And then you just never send the mobile message. So it's very, very simple to track users this way. And it required very significant architectural changes to remove these vulnerabilities. Now that more and more hackers have access to the SS7 network, the interconnect network between mobile networks, this has become commonplace. You can buy, I don't know, 1,000 of these queries for $10 on the internet, and you can track any mobile phone in the world. Try it with mine, and you'll see that I'm in Hong Kong and I'm actually here. But this wasn't the only problem in interconnect. In 2014, a lot of different vulnerabilities were found. So location tracking, I've explained, a byproduct of standard network operations. It's not even a vulnerability. It was specified this way that one network leaks information to another. Nowadays, mobile networks try to prevent this by always responding with the same entity in their mobile network and then taking care of delivering the short message themselves. But this took them years to implement. Another beauty is I told you about the handover feature of mobile networks. So while I'm riding my car, I can travel from one cell to the other and seamlessly my call doesn't break. In order to do that, mobile networks can basically ask for key material, because this also works when I travel when I cross the border. I can set up a call in Germany, visit my friends in Poland, and talk on the way on the phone all the way. And at the point when I'm crossing the border, the Polish mobile network needs to know how to communicate with my phone. So via the interconnect, they would just connect to my network and say, hey, listen, there's a subscriber coming here from your network and he wants to join our network. And he's currently having a transaction, so we need the key. And then my network would just give them the key and say, okay, let's continue the call. So what attackers can do is just at any point in time query your mobile network for the key that it's using, and then use this key to decrypt your calls. Also, a number of fraudulent schemes were identified by my friend Tobias Engel, who managed to change all kind of subscriber records and special features for users. So this is also a significant problem here. And it was introduced by just not introducing security and just relying on this interconnect system, the SS7 system it's called, as a walled garden, just being of the belief that none of the hundreds or almost, I don't know if it's hundreds or thousands of networks that are connected to SS7, I believe it's in the mid-range hundreds, that none of them would engage in fraudulent or evil behavior, an assumption that was proven wrong on numerous occasions. And even if you're not afraid of hackers in this area, you definitely have any international secret service in there trying to fish for your users. So at the 31st Chaos Communication Congress by Carsten Nohl and his team, and by Tobias Engel. So now, taking a step back and looking at these architectural fundamental vulnerabilities that, because mobile networks are so distributed and so well adapted, could not be sufficiently mitigated once the mobile networks were rolling. First attack surface is the authentication. In order to provide for real security, you should implement a bilateral end-to-end authentication scheme. Usually, architects only try to authenticate users and give few or insufficient opportunities to their user to authenticate whether they are connecting to the legitimate service. Best example, of course, is the CA model in TLS connectivities. Also, you shouldn't rely on walled gardens or firewall zones, just saying, oh, nobody can connect to this, so we can offer any service there is, because we just per default trust whoever talks to our service. Another vulnerability is in the specifications. Specify protocols and behaviors thoroughly, especially the corner cases and error conditions, so that you don't get these problems with hundreds of millions of misimplemented SIM cards that leak, essentially leak key material, which they should have never done. And then, I mean, this is nothing new in security. Do not rely on obscurity. Anything you do should be at least, or you should basically be able to open source everything that you do except for the key material. If you rely on anything other than that, you're making a mistake and you will run into problems sooner or later. So why not rely on well-hung cryptographic algorithms that have been tested and deployed by many people to just remove attack surface, even if it is only theoretical. So I hope this was not too dense. These have learned from a couple of years of working in this area, and I'm obviously happy to take any questions.
So are there any questions?
I think there's one over there.
The question is that you're talking about GSM and something like that.
Yeah.
And how about, we have evolved to 4G, 5G, all sort of things. And would that be helpful on that part? Or, sorry, because the infrastructure is there, therefore, on Wi-Fi is a IT thing, they're more or less mobile thing. But my understanding, the 5G, the Wi-Fi will emerge more significantly with the mobile technology, where they switch over all the time, in the sense like that. My understanding is that you have a more small cell approach and you do hop over to the Wi-Fi. Would that part also increase a lot of attack surface or a lot of other security issue over there?
So at first, whenever there was a generation change in mobile networks, problems were solved. So for example, the issue that the mobile phone has no means to authenticate the network is solved in 3G. It is in 3G already. So it's uh, not trivial to provide an IMSI catcher, for example, that offers a 3G network, because the authentication scheme implies that the phone can also always check whether, or it would just break the authentication and the encryption. So 3G active intercept is not a trivial problem. However, when 3G was invented, basically the interconnect protocol stayed the same. So while it's hard to build a 3G IMSI catcher, you still have the SS7 vulnerability that you can get the key material. So this is what made this SS7 research so impactful, that it was a very to attack 3G protected communication. This is, I think, the most significant revolution in mobile networks, because they basically cut off messages or even being calls and moved everything to IP communication, therefore also enabling them to use generally completely untrusted things as Wi-Fi's to offload traffic. So 4G has mainly abolished most of the vulnerabilities introduced here, except for the interconnect problems, which still remain, or of which new ones are to be found in the diameter. However, now they have this challenge of providing service to legacy users as well, and being able to interconnect with legacy networks as well. And therefore, while there is a net reduction in complexity in 4G, the interoperability with 3G and 2G forces networks to just carry on all this bloat, complexity, and vulnerabilities from GSM networks and 3G networks and 4G networks. And then we get to this point where it's just a lot of filthy tricks to make these
So we can take one last question.
Recently, Apple and Android, they start having a new feature called Wi-Fi calling. If you guys any experience spoofing or eavesdropping on Wi-Fi calling feature?
Are you referring to the FaceTime features, or are you referring to voice over LTE? So there's I think you're probably referring to the Apple FaceTime, right? Okay. So that would be Wi-Fi offloading then. So you're using the voice over IP functionality of LTE, and you're using a separate network, right? The Wi-Fi network. I am not aware of vulnerabilities in this area yet, but I'm sure there will be, because voice over IP, let's just say it's not the most beautiful implementation of IP communications. So I think we are definitely going to see implementation vulnerabilities. In all these cases, the system was secure from a theoretical perspective, and the devil is always in the details. So I expect somebody to find vulnerabilities in this area as well.
So thank you, Mr. Neumann. So this marks the end of the conference day 1 of the World Internet Developers Summit. Thank you for your participation, and I hope this had been a fruitful and remarkable day for you all, and that you're able to enjoy yourselves throughout the different sessions of the day. Again, before we end today's program, please return the badges to the registration counter if you're not joining us tomorrow. And at last, if you would like to take the shuttle bus, please go to the place where you got off this morning. One shuttle bus is already ready, and the next one will be at 6:15 p.m. See you again tomorrow at 10 a.m. at Cyberpod tomorrow if you join the workshop. I'll see you in our next event. Thank you. Thank you. Shuttle bus at your destination. Shuttle bus 係金鐘，我哋而家去金鐘，樓下搭個仔個門口。嘢搞到我大嚿，點解啊？好大個喎！點解咁啱嘅？哦，冇嘢。買啦，都唔係我嘅公司。買個 free tag 嘅。